Okay, good morning. We are now on to lecture number 5 on advanced structural analysis. We are still with the topic of basic structural analysis. We are doing a review. We had completed statically determinate structures. We had also looked at the work methods in the last class. We need to complete that portion and then we will do a review of energy methods in this session. As you know, we are referring to this book on structural analysis, and right now we are on to part 3. The focus is on finding displacements in statically determinate structures, but we are also covering related areas. When you talk about work and energy methods, you can actually find the force response as well. So we ended the last class by discussing that there are 3 important theorems based on the principle of virtual work. Historically, these are very important theorems in the development of structural analysis. The Maxwell that we refer to here is the famous James Clerk Maxwell, who made many contributions to physics, and the reciprocal theorems, first contributed by Maxwell and later improved upon and generalized by Betti of Italy, actually gave the first major breakthrough in the analysis of statically indeterminate structures, and they are beautiful theorems. The important point to note is that these theorems are applicable only for linear elastic structures, and unlike the principle of virtual work, which requires you to compute both external virtual work and internal virtual work, here we skip the calculation of internal virtual work altogether. So Maxwell's reciprocal theorem in its modern form basically establishes that the flexibility matrix is always symmetric. Okay, so in the language of flexibility matrices and coordinates, let us take any structure linearly elastic. Let us look at that cantilever frame, and we mark 2 coordinates, and deliberately we have taken 2 different types of degrees of freedom. What is indicated as I is a translation and J is a rotation. The conjugate forces would be a direct action force at I, and Fj would be a moment. Okay. Now the flexibility matrix in this case would be a 2 by 2 matrix, and you can write it like that. The 4 flexibility coefficients are Fii, Fij, Fji and Fjj, and the physical meaning of these quantities are, you can see that if I want to get the first column in this flexibility matrix, then I have to apply a unit load Fi equal to 1, and physically that would be given by this picture. Okay, I apply a unit load at I, and the deflection that I get at the coordinate I is referred to as Fii, and the rotation that I get at the coordinate B is referred to as Fji. This follows from our discussion yesterday. Similarly, if I want to get the second column in this flexibility matrix, I apply Fj equal to 1, which is actually a moment, and the rotation I get at the location where I apply the moment is called Fjj, and the deflection at this I location is Fij, right. So as you recall, Fij is written in such a way that the indices I and j refer to I will refer to the effect location and j will refer to the cause location. So that following that format, it can be proved, and this is Maxwell's reciprocal theorem, that Fij is equal to Fji, and that is essentially And it is interesting because the units of Fij and Fji are completely different in this case. If you look carefully, Fji refers to a rotation, so the units would be radians but caused by a unit force, so radians per Newton in this case, whereas Fij refers to a deflection caused by a unit moment. So it is millimeter per Newton millimeter, and so that is the essential difference, but both reduce to dimensionless quantity divided by force unit of Newton. Now the proof in this case is very elementary. You can prove it using the principle of virtual work. In the first instance, let us compute, or let us establish the principle of virtual work looking at the force field in system 1, that is caused by Fi, and the displacement field in system 2, that is caused by Fj. Then do you agree that the external virtual work would be Fi into Fij? This is force, this is displacement, and the internal work is, you know the units, Mi refers to the bending moment anywhere in that frame caused by Fi equal to 1, so that is the force field, and the other one is the elemental rotation Mj dx by Ei. This we know is true. It is true whether you have elastic behavior or not in general, but to get the curvatures we are using elastic behavior, that is why Ei comes in the denominator. But we can also write another expression for principle of virtual work looking this time at the force field caused by Fj and the displacement field caused by Fi. If we were to do that, then you would write it in this manner. Okay, it's easy to understand. Now if you look carefully at these two equations, you will find that the quantity on the right hand side, which is integral Mi Mj dx by Ei, is the same. There is a commutation between Mi and Mj, but it is the same quantity, and therefore it follows that the quantity on the left hand sides of the two expressions should be same. And since you are applying a unit load Fi equal to Fj equal to 1, it follows that Fij is equal to Fji. A simple elegant proof of establishing the symmetry of this matrix. Now I can choose more than 2 coordinates, I can choose 3 coordinates, and then the size of the flexibility matrix would be 3 by 3, but it will still be symmetric in the sense F13 would be equal to F31, F23 would be equal to F32, and so on. So in summary, in a linear elastic structure, the displacement Fij at coordinate I due to a unit force or unit load acting at coordinate j is equal to the displacement Fji at coordinate j due to a unit load acting at coordinate I. Now the load could be a force, it could be a moment, and although we proved this for a frame, you could prove it for a truss as well. There the force would be an actual force if it is an internal force. Now let us just demonstrate this with a simple example of a cantilever beam. Let us look at the 2 coordinates referring to the deflection and the rotation at the free end. If you were to derive the flexibility matrix, you could do that by first applying a load P at the free end and then applying a moment m0 again at the free end, and you can use any method. You could even use conjugate beam method to work out the deflection and the slopes, and those values are very easy to calculate. The deflection, you know, caused by the load P is PL by 3 Ei, the rotation is PL squared by 2 Ei, and due to the moment the deflection is m0 L squared by 2 Ei, and the slope is m0 L by Ei. Now if you were to write these expressions in a matrix form, this is how you would write it, right? And you will notice that you can separate out P and m0 into the load vector, and the coefficient matrix turns out to be a property of the structure independent of the loading. You can put in any value of m and m naught, and still that flexibility matrix does not change. So, it is a very useful property of the structure, and it is very evident that the matrix is symmetric, and that is a proof. Okay. Betti moved further and gave a more generalized expression of the reciprocal theorem. It is reciprocal in the sense the effects are reciprocal. Okay. And here Betti talked about the entire system. So, you look at the force field system 1 and the conjugate displacements. So, you look at both the force field and displacements, but you need to look only at the joint forces and displacements. Do not worry about the internal forces and deformations. And let us say you have the same truss or the same structure, but a completely independent force and displacement field. So, we will label this as system 1, the top one, and the other one as system 2. And this is Fj1, Dj1, and this is Fj2 and Dj2. And if you invoke the principle of virtual work, you can easily prove that if you multiply the joint forces in one system with the joint displacements in the other system, obviously there is no correlation between the two, there is no cause effect relationship. We call it external virtual work, but it is really virtual. I mean, you are just multiplying a force with displacement disconnected with that force, but at the same location in an identical, in a clone of the same truss. That product is equal to the summation of the forces that you would get. I mean, this summation product, if you were to multiply the forces in system 2 with the conjugate displacement in system 1. Okay. So, this is really reciprocal, not only in terms of displacements, but also in terms of forces, and this can be easily proved. You will find that the Maxwell's theorem is a special case of Betti's theorem when you have only one load acting, and if you make it a unit load, you get the relationship Fij is equal to Fji. Put together, the two reciprocal theorems are often referred to as the Maxwell-Betti reciprocal theorems. So, if you want a statement of the theorem, it would be the total external virtual work associated with forces F1 in system 1 and the conjugate displacements D2 in system 2 is equal to that associated with forces F2 in system 2 and the conjugate displacements D1 in system 1 in a linear elastic structure. Now, the word conjugate has a special meaning. It comes from the word conjugal, which really refers to a marriage between a force and a displacement, but they really refer to the same coordinate location. Okay. So, let us now see a demonstration of Betti's theorem. The first application of solving statically indeterminate structures. Here you have a two span continuous beam, and let us say that, so it is externally indeterminate. You have two equations of equilibrium to solve three vertical reaction unknowns. So, let us assume one of them to be the redundant, and here we have chosen the middle reaction Vb as a redundant X. Now, we will call the first picture as system 1 and the second picture as system 2. System 2 is virtual. In this system, we allow a movement of that support X, and you will see that the deflected shape would be like that of a simply supported beam supported at A and C, and let us say those reactions are Ra, Rb and Rc. So, we will refer to the deflection under the first load location as delta P here, and the deflection or the support settlement here is delta X. So, you have got displacements and forces in system 2, and you also have displacements and forces in system 1. We now invoke Betti's theorem, and you will find that the total external virtual work that you get when you multiply forces in the first system with the displacements in the second system is just P into delta P. Do you agree? Because none of the other external forces have any support movements that are non-zero. So your left hand side of the equation is P into delta P. But you also have X doing work, right? This X doing work, and X does negative work because delta X is in the opposite direction. So we would say the total external work is P delta P minus X delta X. Now you take the external virtual work caused by the forces in the second system with the displacement in the first system, and you will find that that product is 0, because there are only 3 forces here, RA, RB, RC, but they refer to supports in system 1 and none of the supports are moving. So it is a beautiful equation. You end up by discovering that X, the unknown X, is nothing but P into delta P by delta X, which means if you take the ratio of this deflection to this deflection, and that ratio times P is the amount of force that you get in this reaction. That is a fraction of P that is passed on as a reaction in the middle support. And actually in the early days they did measurements to prove it. Actually you can do this physically on a beam and measure the deflection, and that is your reaction. So it is a simple initial way of understanding indeterminate structures, and if you really had an exact solution to those deflections, and you can derive those by any of the methods that you know, including direct integration, conjugate beam method, virtual work method, if you have an expression for delta X and if you plug in the value of X equal to L by 2, then you can actually get the exact solution, which in this case turns out to be 11 by 16 P. Okay. But even if you did not have the exact solution, you get an approximate solution by just learning how to draw deflection diagram reasonably accurately and scaling them. So just wanted to show you something of historical value. Today we do not use those old methods because we have very powerful methods of finding unknown redundants. Mueller-Brislow's principle is a powerful principle, and it is credited to both Mueller of Germany and Brislow, I think, of England, who more or less at the same time came up with a powerful principle which helps us draw influence line diagrams. As you know, the influence line diagram is a diagram that is especially useful in finding a response quantity caused by the movement of a unit load along the length of the beam. It is useful in bridge design, it is qualitatively useful in building design as well. So here I have a 2-span continuous beam. I have positioned a unit load 1 which can occupy any position along the length of the beam, and I wish to find, for example, the support reaction RA. What do I do? Well, if I want to use Bette's theorem, then in the second system I allow for a displacement where RA is acting, which I can achieve by actually removing that support and deliberately applying a force Fa. So you agree that we get a deflected shape roughly as shown in this figure. Now if you invoke Bette's theorem and you refer to this deflection under the unit load 1 in the first system as delta X, then you can show that RA into delta A, this RA into this delta A minus 1 into delta X minus, because the two are in opposite directions, must be equal to 0. And so it follows that RA is equal to delta X by delta A, and that simple equation has a powerful meaning. It basically says that if you want the influence line for the vertical reaction in this 2-span continuous beam, if you want the influence line for RA, all you need to do is to remove the restraint, remove that support, lift up the beam by a unit displacement. If you put delta A equal to 1, then whatever deflected shape you get is the exact influence line diagram for the reaction. So that is a very powerful principle. And even if you were not to put a unit displacement, you gave it some arbitrary displacement, then the shape that you get represents the influence line diagram to some scale. If you normalize the deflection so that the deflection is unity, then you get the exact influence line diagram. And this can be proved for any response function. It could be applied to bending moments, shear forces, and so on. So it's a very beautiful principle called the Mueller-Brislo's principle. So the statement would be the influence line for any force response function in any linear elastic structure is given by the deflected shape of the structure resulting from a unit displacement corresponding to the force under consideration. And an interesting thing to note, and I want you to give me the answer for this, is that if the structure is just rigid, if it is statically determinate, the influence lines are always straight lines. If they are indeterminate, as in this case, they are not straight, they get curved. Why is that so? It's a good point to reflect over. Why is the influence line diagram for a continuous bridge made up of curved lines, but for a simply supported bridge they are all straight lines? Yes? Yeah.
For statically indeterminate structure, if you give a displacement which is equivalent to some indirect loading, there will be bending moments coming into the picture which will cause
Okay,
in the deflected shape, and so the influence lines are there.
Yeah, that's one way of arguing it out, but perhaps a more simple way is to go back to the realization that the force field is related to the displacement field. Structures are statically indeterminate because they are over rigid, they are over constrained more than the minimum required, right. So if you remove those additional constraints, you get back a just rigid structure, and if you remove a constraint from a just rigid structure, then it becomes a mechanism. Do you understand? If you take a simply supported beam and you remove one support and you move the structure, then you have a rigid body. It behaves like a mechanism. Is it clear? But if you had a two-span continuous beam and you removed a support, it's still statically determinate, it's still just rigid, it can still take loads. So that's the difference. Is it clear? So your answer is also correct. So that's another way of looking at it. Right. Quickly, it's nice to qualitatively draw influence lines diagrams. It's very easy. If you want the influence line for the support reaction of a propped cantilever, you just lift it up. If you can write the exact expression for y of x, which is now possible because you have many techniques of doing that, then you actually have an equation for that influence line. And I would like you to try drawing the shapes of the influence line diagrams qualitatively, okay, just the shapes for RA, RB and RC quickly. Just draw the shapes of the influence. RA we have already drawn, okay. Can you draw the influence line diagram shape for RB and RC? Just the shape, and the value will be unity at some location. You draw it and you compare it with the answer that I am going to show you. This is one diagram, okay. This is the diagram which we did in the previous problem. This is for RA, agreed? Why is the value negative in the sector BC? What does it mean? What does it mean to have a negative value?
So it is sagging. So the BC segment will be sagging.
The beam segment in BC will be sagging. So what does it mean for RA?
Because it is sagging.
Yeah, so there is an uplift, you can visualize it. The beam wants to lift up, it's not, you said the wrong thing, it's not sagging in BC that will cause the reaction, it's a hogging in AB that wants the beam to lift off from the support A, and so you need to pull it down, and that is why you have a negative reaction. Is it clear? Try drawing for RB. Will you have anything negative if you? No, because you just lift it up. So RB is very straightforward. Okay. What about RC? Similar to RA. Okay, so it's quite easy. Now, if you want the exact equations, you have techniques of doing that. Okay. What about? So the exact equation, for example, is something you can generate, and there are handbooks available where they do not give you exact equation, they are useful in bridge design, where you get the ordinates at different locations, you divide the span by about into 10 segments and you get those locations, and they are sometimes used in practice. Now look at this beam, it is called a balanced cantilever beam. I think we looked at it last year. Will you get curves or will you get straight lines if you were to draw? So in this case you get straight lines. But you can still use Mueller-Brisloff's principle. Now I have marked here locations G and H and J. Can you try drawing the influence lines for the bending moments at, let us begin with J and then G and then H. So what you need to do is to find the influence line for MJ. What should you do? You put an internal hinge there and move it either up or down. If you move it up, then you will get positive values, which is what you should get for sagging moment. So you should follow a sign convention, but you can also try drawing and getting the support reaction at A and B. Can you try that? Influence line for support reaction at A and B and so on. It is very easy, you remove the reaction at A and you lift it up. How will this move? So we have done this earlier, you get a series of lines, they are very easy to do, they are all straight lines, and once you catch one value you can catch the rest of it. So we have done this earlier, so I would like you to recall what we did. Okay. With this we wrap up virtual work and work theorems, and we go straight away to the next topic, which is energy methods, right. Now specifically we look at energy methods that help us solve problems of finding unknown forces that need to satisfy equilibrium, and also energy methods that will help us find out unknown displacements, right. So mostly we will be using Castigliano's theorems, which you have heard of, 1 and 2, but it is good to know the origin of these theorems, and they come from the principle of stationary total potential energy and the principle of stationary total complementary potential energy, and they have very wide applications. Energy methods are not usually very well understood by students, it takes time to really understand. So let us do a quick overview. Now you recall I had asked you this question earlier, if you have a cantilever beam for example, and if you have a mass at the free end, you can replace the beam with a spring, both have elastic behavior, and let us say the static deflection is delta static. In the undeformed configuration you have potential energy in the mass but no elastic energy in the spring, and both are forms of potential energy. And in the deformed position you have the mass has lost some potential energy and the spring has gained some potential energy, that is elastic potential energy. The other one is the gravitational potential. Are these two quantities equal? Are you convinced that the answer is no? Because we have heard about the principle of conservation of energy, and they should be equal. The loss in potential energy in the mass should be equal to the gain in elastic energy in the spring. Am I right or wrong?
Yes,
but you will find that when you do the calculation.
No, but if it would be an ideal system, then it would have some velocity.
That is the correct answer. You really do not have a static equilibrium position. It is like a pendulum, pendulum moves back and forth. So unless you stop it, if you stop it, and it will stop on its own due to various dissipative forces, due to friction, right, and that energy is lost. So the same thing happens here. This, if you work out the calculations, the loss in gravitational potential energy is mg delta static, and the gain in strain energy in the elastic spring is half mg delta static. So there is a half which gets lost, and that is the energy dissipation that you get. And so if you really had an ideal system, it will not lose any energy, it will actually gain maximum velocity at the so called static equilibrium position, and it will move down further, but then you are violating static equilibrium. So the spring will move back, it will move back and forth, it will keep tracing the path up and down on that P delta curve, and you can prove that the dynamic displacement, the total displacement that you get will be 2 times that of the static displacement in an ideal system, right. But our real systems are not ideal, there is going to be dissipation of energy, and if you really want to model it, you should put a dash pot which takes care of the dissipation energy. And so we make one big assumption. So the graph that you see here shows simple harmonic motion, but in reality we know that things come to a stop, and they come to a stop fairly quickly, right. So instead of loading it suddenly, we simulate in our minds the concept of gradual loading under adiabatic conditions, which is called static loading. That means in our minds, let us assume that it takes a long time to gradually load the beam, so slowly that there are no accelerations in the beam, and we reach the same static deflection. So there is a nice concept called strain energy density in a material, and that is referred to by the symbol mu. It is really integral sigma d epsilon. It is a measure of strain energy per unit volume in an elastic material, subject to gradually increasing strain under adiabatic conditions. Okay, there is no heat transfer assumed. This means that there must be no heat flow through the system in most situations. In elasticity, however, the reality is somewhere in between isothermal, which means constant temperature, and adiabatic. With this assumption, if you integrate the strain energy through the volume of a bar, let us say subject to axial tension, then you get the classic equations of half comes if it is linear, half integral axial force times strain integrated over the length of the bar. Okay, so there is another term which is called complementary strain energy density, and here you visualize the incrementing of energy coming from an increment in the force or the stress rather than in the displacement. You can do loading either displacement controlled or force controlled. So if you do it force controlled, then the product, which is also energy, would take this form, and we refer to it as mu star, and it is the other complement of the rectangle which contains the total energy. Sometimes it has a physical meaning, often it does not. So now let us not worry about strain energy density. Let us talk about absolute strain energy. Let us talk of a non-linear elastic system where you can prove that the total strain energy is the area under the curve when you have gradual loading, and ideally you can visualize strain energy as a form of internal energy in an elastic system as the work we need to perform in order to lead the system gradually from the undeformed configuration to the deformed configuration. And so the energy depends only on the initial and final configuration. In a truly conservative system this is true, it is called a point function, and when you return the path of that curve is completely retraced and that energy is totally recoverable. The complementary strain energy is a complement to this energy. That means if you take the area of the rectangle and you subtract this energy, what you get is U star. Now let us talk about linear elastic behavior. In fact that is what we will deal with most of the time unless you have non-linearity. The beauty in linear elastic behavior is these two terms are interchangeable. U is equal to U star is equal to half the maximum force times the displacement, and what we need in structural analysis is how to compute strain energy and complementary strain energy in beams and frames and trusses and torsional members and so on. So you have axial strain energy, this is the expression. You have two forms. In one form you express it in terms of the displacement or the strain, in the other form you express it in terms of the force. Both are equal, U and U star. This is the expression for a truss which is made up of many members. So you just have to add up the strain energies in all the elements, and you are familiar with this, the factor half comes. This is the strain energy in a beam or in a frame where you are concerned only with flexural strain energy, U and U star. This is strain energy caused by shear, which is usually neglected. We will see later that it is not always negligible, and you have the torsional strain energy. Okay. Now in all these expressions you will find some rigidity terms appearing. For axial strain energy the rigidity term is EA, it is called axial rigidity, a product of the elastic modulus and the cross sectional area. For the bending term you have EI, which is flexural rigidity, it is a measure of the stiffness, it is a product of the elastic modulus and the second moment of area. For shear rigidity you have GA dash, and that gives us the shear strain energy, and GJ for a prismatic circular section, J is the polar moment of inertia, she is the shear modulus. For non-prismatic sections and for non-circular sections you do not have a case of pure torsion, you have warping coming into place, you have some distortion coming into place. So very quickly, if you have a force, axial force, the corresponding displacement deformation parameter is elongation, you are familiar with the straight line behavior. This is what you get in a truss member. In a beam, let us say a beam subjected to constant bending, the radius of curvature is constant, so the angle subtended is theta naught, so theta naught is curvature into L, and so the conjugate of bending moment is rotation, and the slope of that line is EI by L. So EI by L is a measure of flexural stiffness. In the first picture EA by L is a measure of axial stiffness. If you do not have uniform moment, then it is some EI by L into some multiple, some 2 or 3 or 4 or 5 or whatever. Similarly here, if you are talking about shear strain energy, and let us say you have a beam subjected to constant shear force, then the shear deformation is delta naught, which is the shear strain gamma, which is constant for that segment into the length of the element, and the slope of this, which is a measure of shear stiffness, is GA dash by L. Where are these terms used? You know about shear walls in buildings, right? If you have a very tall building and the wall is narrow in length, then it will behave like a beam. So you have mostly flexural strain energy. If you have a short squat shear wall and it resists lateral load, then the predominant energy would be shear strain energy, okay. And if you have a wall which is of intermediate size, then you have both these stiffnesses coming into play. So if you want to be exact, you should not ignore shear deformations and include their effect. Similarly, the displacement the deformation that you would relate with torsion would be the angle of twist, and the slope of that line, here is a shaft subject to pure torque, is Gj by L. Next question, if I have a beam or any elastic body, and if I apply some load and it has a strain energy U1, then I applied independently some other load and it has a strain energy U2, and if I apply both these loads simultaneously, would the total strain energy be U1 plus U2? Why not?
Because there will be.
So
on the graph we can.
So you can understand this when you draw a graph, you are right. You will find that the two triangular areas caused by F1 and F2 are what you would get independently U1 and U2. But you have to take the total area under the curve, which includes this rectangular segment. What does that area represent, that rectangular area?
So
of the first system that does work on the second system.
Right. So you first applied a load F1 and the system underwent a deformation D1. Then you applied F2 and F1 is also going to move, but not caused by itself, but caused by another agency F2, and that movement does not have a cause effect relationship, so there is no half coming in, so it is a solid quantity. So that is the portion that we tend to miss out, and you can prove that additional strain energy delta U is square root 2 times square root of U1 and U2. This can be easily proved. Now the standard problems that you need to know is how to compute strain energy in any truss, in any frame, in any beam. So very quickly we will go through this example, we have done this earlier. Let us say you have a frame, it is a cantilever frame, it has got this loading, we have earlier calculated D1 and D2, now we want to find out what is the strain energy in the system. So let us do it exactly, that means let us compute all the strain energy components that is possible. A frame will have in general bending strain energy, shear strain energy and axial strain energy. Now please note, we are actually computing the complementary strain energy and we are invoking the principle that is numerically equal to the strain energy. So the formulas are half integral m squared dx by EI plus half integral s squared dx by GA dash plus half integral n squared EA by dx, representing the bending, shear and axial strain energies. One question I need to ask is, why do we have GA dash? What is this A dash? A dash is a reduced area of cross section. Why don't we take the full area of the rectangular section?
Total area is not subjected to total shear stress, maximum shear stress. You should take the average of it.
That's right. You see, under flexure you have non-uniform shear stress. It's not like direct shear where you have the uniform shear stress. If you had direct shear, you could use GA, but you have non-uniform shear stress, and you can prove that you have to get an equivalent area, and it's usually a reduced area, and it's that area divided by 1.2, for example, for a rectangular section, and that factor is called a form factor. Okay. So let us quickly do the calculations. You have a rectangular section, it is easy to calculate I, the second moment of area, is B d cube by 12, the area is B into D, and the reduced area, the shear area, as A divided by 1.2 for a rectangular section. The elastic modulus E is given to you, and the shear modulus is E divided by 2 into 1 plus mu, which is Poisson's ratio. So you have those two material properties. Then you can find the three rigidities just by multiplying. E into I will give you flexural rigidity, E into A will give you axial rigidity, and GA dash will give you shear rigidity. Okay, we will just quickly go through the concept. We have done this earlier. Your first job is to analyze this frame. You can easily draw the free body diagrams and then draw the bending moment, shear force and axial force diagram. We have done this earlier. You can use these three diagrams one at a time to actually compute the energy quantities. Let us take flexural energy. So this is your bending moment diagram, which, and we are going to prove that the flexural energy is the predominant energy. You can do this integration. It is integral m squared dx by EI. You have to do it in parts because the bending moment diagram is changing, and you can do it. This is a hard long way of doing it. Is there an easier way of calculating this? Yes, you can use volume integral, you can use the area multiplication method, and it is much faster. Okay. Let us take the second case, which is shear strain energy. This is very easy to do by the area multiplication method. You just have to multiply this diagram with itself, and then you also have the axial strain energy, and you have the three quantities, and when you add them up you will find something very interesting. That is, the bending strain energy here is 109.705 Newton meter, shear strain energy is only 0.58 and axial strain energy is only 0.30, and the total is 110.6. So you can clearly see that you can ignore shear deformations and axial deformations. It is like assuming that the shear rigidity is infinite and the axial rigidity is infinite, and that is the reason why this assumption that we frequently make in structural analysis when we deal with frames is justified. But there are exceptions, and if you want to be accurate you can include those effects as well. In matrix methods we will do problems where we can do this more exactly. Now one of the theorems which is sometimes very useful to apply is this concept called the external work done when you load a system gradually to it from 0 to its maximum value will be equal to the total internal work. Okay. Remember, if it is a linear elastic system, the factor half will apply also to the external work. Okay. This is different from virtual work, this is real work, and so if you invoke this theorem, and you can prove it very easily using the principle of virtual work, because the principle of virtual work just says the total external virtual work is equal to total internal virtual work. Here you are referring to the force field and displacement field in the same structure with a cause effect relationship. Now if you multiply both sides of the equation by half, then you will notice that what you get on the right hand side, the internal virtual work times half, is nothing but elastic strain energy. Is it clear? And so that is why the strain energy is exactly equal to the external virtual work. But if there is some initial strain energy locked into a system, and often you have that, for example when you load rolled steel beams you have some residual stress locked into the beam, then actually you need to subtract that part because it is only the incremental change in energy that you are measuring and you are calculating, and you can actually prove Betti's theorem using this formulation. And if you apply one system first and then the other system, and you change the sequence and you write the two expressions and you compare the two expressions, you can end up proving Betti's theorem. So this is an alternative proof. So you can prove Betti's theorem either following the path of the principle of virtual work or invoking this energy theorem, and similarly you can prove Maxwell's reciprocal theorems. Okay, and the proof is clear. We will stop here. Thank you.